let us see how gravity is understood in classical model of universe. It all started with Newton's theorem, wherein he defined gravity as a force of attraction between the two masses, which was directly proportional to the masses in consideration and inversely proportional to the square of the distance which separates them. This in turn was superseded by theory of general relativity from Einstein. And still, why do we keep it? Because it's a good approximation of mass, the way it behaves on planet and many planets in the solar system. It is just that there were these major aberrations where Newton completely discounted for the fact that space exists and that he could not explain the aberrations in Mercury's orbit. And that is when we come to Einstein's general theory of relativity. What he suggested is that massive masses in the universe have the tendency of bending space around them. And that bent space in turn guides the smaller masses as to how to move. Now this tandem or tango of mass and space leads to a gradient which we know as gravity. Now you may say, Einstein has already addressed space in the equation. Why is it that we are coming up with another theory again based on space? How radically different these theorems look, but we will realize that they are on the same side of the fence. They are trying to qualify and justify the existence of gravity, whereas what we are saying is gravity does not exist. If you see, the common factor in these two theorems is that larger the mass, stronger the influence. What I mean by influence is the gravity itself. Farther the mass, weaker is the influence. Whether you take Newton's theorem or Einstein's theorem, they are the same. Now coming to Einstein's theorem and aberrations. In real life, they have not been able to find one. But imagine a situation wherein you see that, as is said, that the strength is the greatest strength is the greatest weakness. In this particular theorem, the greatest strength of this theory is the gradient itself. And this gradient exists because of different masses coming into picture. What happens when this mass is exactly equal to this mass? Let us consider our own solar system. Remove all the planets from the solar system. Let's have just the sun as our mass. It's the only mass in the universe, let us consider. Let us do Ctrl+C, Ctrl+V, which is, let us create a twin, exact replica of the sun, which bends the space exactly the same way as our own sun. When they come near each other, what would happen? Thanks to this gradient, the massive mass detects the smaller masses. It's like a radar scanning. Anything which is coming and getting affected because of this gradient is guided by, guides the space, the planet in turn. But what happens when these gradients are exactly similar? When they come near each other, would they just slide by? These are the kind of aberrations. Of course, such a thing never happens in the universe. You will never, at least at the galactic stage, get two masses which are exact replica. But we are talking about theorems. Theorems should be able to handle in any case.
In classic model of universe, when you started with Newton's theorem, he completely discounted space as a factor, and it was very difficult to establish a theory as to how these two planets would communicate because there was no space. So when you add or remove or rearrange masses in a solar system or any for that matter any planetary system, the resultant chaos was unexplained. This was improved in case of Einstein's theorem, wherein it was suggested that massive masses have a tendency to bend the space-time around it, and that bent space leads to a gradient. That gradient is the one which is going to guide all the small masses which are going around it. So the communication was easier because there was a gradient, but the issue was a hypothetical case wherein there are twin masses. In the sense, there are two masses which are exact replica of each other. So that means both are having the same influence or bending the space to the same extent, and hence would they, when they come near each other, would they be blind to each other and just glide by? Or for that matter, when you have these smaller masses, planets which are of the same mass, would they just roll off the fabric of space? So now let us understand how spacity helps planets communicate. The good thing about spacity is you do not need a gradient for communication. The mandate of space itself establishes a communication. The space is supposed to bring the masses together, hold the masses together, bring the masses together and act on them. That itself establishes how the planets are going to communicate. They will be communicating through the space forces S1, S2 and S3. And when it comes to the nature of masses, as we have seen in space, the spacity theory, if they are twin masses, it would not bother. It would just bring them together. The play of S2 would still act. Whether they are same masses, it would still hold the solar system together. Whether the masses are in static condition, motion condition, whether there is a massive sun or a massive mass at the center or a not so massive mass at the center. Like in the case of solar system, you have a massive mass, comparatively massive, whereas in galaxy you have a comparatively less massive mass at the center, or no mass at the center at all. It would still be able to handle such theoretical effects. And one thing that we should understand here is that two bodies, whichever bodies that you take, they never exist in isolation in the universe. Whenever you measure a value that these two masses are coming together, you cannot discount the effect of the universe on these two masses. The measured values have a component which has the effect of the universe already built in.